Good afternoon, everyone. Welcome to the interactive session 11. So, as you all know, this is the interactive sessions that we are conducting for NPTEL course Experimental Physics second module. Course instructor is Professor Amal Kumar Das from IIT Kharagpur, and I am Rinalini, PMRF Research Scholar from School of Physics, University of Hyderabad. So, as I said, this is 11th session, and just to repeat, already you guys know, we have these sessions of 2 hours every Saturday, 3 to 5 p.m., where we discuss kind of revise and briefly whatever the topics have been covered by professor in that week, and then we discuss if there is any doubt, and also numericals based on those topics. So that is what we'll do for this week as well. So first, like always, let's have a brief recap of what were the topics that we had discussed last week. So last week we had started discussing plane transmission grating. So after we understood interference, diffraction, and various other phenomena, so we had started discussing about single slit diffraction, Young's double slit experiment, and similarly double slit diffraction, and that we get interference and diffraction based patterns there. After that, we had discussed this diffraction grating, which is basically n-slitted obstacle. So that's what diffraction grating is. And then we had discussed that there are two types of gratings. One is one through which a transmission happens, and another one is reflection grating. So basically work is same, only for transmission, light transmits, diffracts, and we get pattern on another side, whereas for reflective grating, the light is incident and gets reflected back, and the diffraction pattern is obtained on the same side. So this is the difference. And then we had discussed the conditions, principal maxima and minima. Then we started discussing polarization, that we have light, which is an electromagnetic wave. It has electric field and magnetic field components which are perpendicular to each other, as well as to the direction of propagation of light. And then the electric field component of light is in all directions. So when we restrict it by some means to only one plane, then we call that polarized light. And then we represent unpolarized light by something like this, that the electric field component is in all directions. And when we want to say it's polarized, if this is the direction of light, say, then we say the electric field is plane polarized. The light is plane polarized, electric field component is varying only in this direction, or also we can say it's only varying in this direction, perpendicular to the plane of the paper right now. So these are the symbols by which we show that that the light we are talking about is polarized and the light we are talking about is unpolarized. Then we had talked about double refraction that happens in certain kind of materials like calcite and quartz, which are uniaxial anisotropic mediums, and calcite is negative, quartz is positive, uniaxial anisotropic medium. And then what is the difference between them? Then we had understood that we get ordinary ray and extraordinary ray, which we call O ray and E ray respectively. So this is the double refraction that happens by birefringence. It happens through these special anisotropic materials, because there is one ray which follows the usual ordinary Snell's law or law of refraction, whereas there is another part of it that undergoes some deviation, it seems, and that's why we call it extraordinary ray. And then we get polarized light out of it. If we send unpolarized light outside, we get polarized, but their polarization is different. For ordinary ray, the plane of polarization is perpendicular, like you can see, so we call it sigma polarized, whereas E ray is bipolarized, that is the polarization is like this, that electric field component is varying in this direction in the plane itself. And then we had discussed a little bit in detail the E ray, O ray, that along the optics axis, the speed of E ray O ray is same because refractive index is same, whereas in other directions their speed there is difference in speed for O ray and E ray. So polarization by double refraction we had discussed. Then what are the applications of these birefringent material? That we can make something known as Nicol prism, which is an optical device through which when light passes we obtain, when unpolarized light passes through this Nicol prism, we get polarized light out of it. So this is one use of it. And then we can make Racon prism, Wollaston prism, and retarders, which will give us quarter wave plate, half wave plate, and so on. Then polarization of light. Then further we started discussing something known as Malus law, that when unpolarized light is sent through a polarizer and the we want to get the intensity of it, intensity varies as I naught cos square theta. This is known as Malus law. Then we also discuss it Brewster's law, that polarization of light can also happen by reflection from a medium, but it's at particular angle. Like see, if this is a glass slab or some material and we are throwing light incident on it, then it will reflect or refract, but there is particular angle at which there is the reflected light, there will be some reflection, and the reflected light will be sigma polarized and refracted light will be unpolarized. So this particular angle is known as Brewster's angle, and it's tan inverse of refractive index of that material, that Brewster's angle value. And the angle between reflected at this particular condition, the angle between reflected light and refracted light is 90 degrees. Okay. So this was what we had discussed last time. Now let's this was little part that I thought I can discuss again. Last time maybe we had missed was just polarization of light, and again it includes what do we mean by polarization of light. So we had discussed just now as well that all light sources emit unpolarized light. What it's showing here is direction of light is this, as you can see. An electric field component, why we are not showing magnetic field component, although both the components are always there. As you can see, this is the direction of light, and there is electric field component variation, and perpendicular to it there is magnetic field component also varying. But because the strength of magnetic field is very very small than electric field strength, thus we can safely ignore it and we just represent electric field. That is sufficient and safe for us to do. There is no issue with that. So here also these arrow mark shows the direction of electric field component variation. Right now this electric field component is varying in all possible directions. So right now it's unpolarized. Okay, now when we pass it through some special kind of material, after which it becomes polarized, and we call that material polarizer. Okay, and it has some use. These kind of why we need polarization of light, like you can understand a daily life example when we use some glasses, sunglasses we call them, right? So those sunglasses have these kind of polarizers through which if sunlight is coming or any light is coming, then its intensity decreases. Why? Because electric field component only restricts in one direction and not in other direction. So we want some light, of course. Why? Because I want, even after putting on a sunglass, we want to see the things around, right? So we cannot just keep an completely opaque object over our eyes. But we don't want too much brightness. That means the other components of light, if we can avoid, then we will get the required amount of light through which we will be able to see the objects around, but it won't be glaring on our eyes. So that's one example where this polarizer has application, and very important application, as you can understand. Similar way in other places also we use polarizers and then analyzers, which are the same thing. It's just after polarization of light we put something which we call analyzer, because now we can analyze how much polarization has happened. So we'll discuss that also further now. So then how we can produce polarized light? As you saw earlier, we were talking about using these Nicol prism through which E ray O ray will pass, and E ray will get sigma polarized, or O ray will get some polarization. So that is one way. Then Brewster's angle, we just now discussed that after reflection we will get polarized light. So these are certain ways through which we can do polarization. This is also just explained. We have explained bipolarization. As I said, electric field component is varying in the plane itself, but here sigma polarization we call when the electric field component is varying perpendicular to this plane. Okay, now these are four methods through which we produce polarized light from an unpolarized light: dichroism, scattering, reflection, birefringence, double refraction. This we have discussed. Reflection is Brewster's angle that we discussed, and birefringence, double refraction. Yeah, E ray, O ray. Okay. Now scattering, where sunlight scattering, like in atmosphere we have some molecule which scatter these lights, and because of that we get them as polarized. This happens in nature, and there are materials which are called which show dichroism. They are naturally occurring, but what happens is they have a differential optic axis along one direction, through which when light passes, unpolarized light, when it passes, we get polarized light on other side. Only we need to take care of the optics axis alignment. So these are natural things, natural occurring crystals. In reflection birefringence, we make the material in such a way that we get, or we follow certain conditions so that we get polarized light. So experiment for O ray and E ray. If we want to conduct an experiment to determine refractive index of that material, now we know that along the optics axis, the refractive index, and that is the speed for both O ray, E ray is same. Okay, but when it deviates from parallel to optics axis to any other direction, refractive index for O ray, E ray changes, and that's how the speed for O ray, E ray changes. So I am using some material, okay, which is a birefringent material. That means for O ray and E ray, refractive index will be different. So we now, for that material, we want to determine refractive index. NO means for ordinary ray, and refractive index for extraordinary ray, that is E ray, and we are using a calcite crystal. Okay, so this is we want to determine. This is the experiment. Now recalling that when we were using a glass prism and we wanted to find out its refractive index, we were using this formula that we had derived also. So this for this you can watch the previous videos. I think some fourth week or third week we had discussed these things. So we were using this formula which says that refractive index is given by sine of A plus delta m naught by 2 to the ratio of sine of A by 2. Here A is angle of the prism. So here we are using this material we are putting in a prism shape, and we are using that to find out this. And here A is angle of this prism. Okay, and this is deviation of angle. If you remember, like if there is no prism, then this incident ray will just go in this direction, right? And detector will detect it here. But because of this prism, there will be refraction here, and then again on this interface there will be another refraction, and thus the light, instead of going in this direction, will be deviated along this direction. So the angle deviation from original path to final path, this angle we call deviation. This is just to recall, we have discussed this in quite detail earlier. And this will be different for O ray and E ray because the refractive index of the material is different for them. So we want to see what we will get, but this is the formula that we will be using to do the same. And using this, so again the spectrometer, if you remember on the table, we'll keep the prism, we'll make incident light, and then using spectrometer we'll measure where is the intensity we are getting. Then we'll see how much angle deviation is there. From that we'll get angle of prism also we'll measure, or maybe it is known, and then deviation we'll get to know. then just putting in this formula we'll be able to calculate. So this was the basic of how to find out the angle, determination for O ray and E ray separately when this happens. Okay. Now let's discuss about polarimeter. So there is a particular kind of equipment or instrument called polarimeter that we use to find out. Okay, so let's first talk about specific rotation, or right now I was telling that we make incident unpolarized light on some special kind of material, and what we get out of it is a polarized light. And this particular phenomenon has a lot of applications, that also just one daily life application we discuss. So this is important. Now there are certain natural items, natural materials in nature, which what they do is, if, as I said, unpolarized light means the electric field component is varying in all the possible directions, and polarized means the electric field component variation restricts to one plane. Now we have certain materials which, if I have kept here, say this is some beaker or something transparent, inside that I have kept that material. I'll let you know what kind of material that is. So I've kept that material, and now I'm making incident this plane polarized light, means its electric field component is varying in particular direction. Now when it will come out and pass through this particular material that we don't know yet, it is some material, then this direction of light will remain same, but the plane of polarization of electric field will change. How much it will change, that depends on the material. Okay, we'll see how it depends, what is the relation, but it changes the plane polarization angle. Earlier it was like this, now it has changed to this, or maybe it can become perpendicular also, something, it changes. These kind of materials are called optically active material. Okay, and depending on what kind of material it is, it may turn or rotate the plane polarization to right or left. So accordingly they have different name, but basically we have to keep in mind that these such kind of materials exist, and we call them optically active. And example is cane sugar. So if we have cane sugar juice in this transparent sample holder, and we'll incident polarized light through it, then its angle of polarization will change. Okay, so the specific rotation that we define is a property of a chiral chemical compound, or we can just, for our discussion, we can simply call it optically active compound. It is defined as change in orientation of monochromatic plane polarized light. So as I said, it's plane polarized. So change in orientation of monochromatic plane polarized light per unit distance concentration product, we'll see what this is, as light passes through a sample of compound in solution. If a compound is able to rotate the plane of polarization of plane polarized light, it is said to be optically active. Okay, said. And we'll see what do we mean by per unit distance concentration product. So yeah, so this kind of instrument, polarimetry, a polarimeter is an instrument through which we can determine how much that rotation has happened, how much the plane polarized light has rotated. That equipment is called polarimeter. Okay, so again, to get this definition of specific rotation, we define it as optically active substance solution is, we define specific rotation for optically active substance and solution of it. Okay, and this is defined as the rotation of plane polarized monochromatic light of wavelength lambda produced by a column of solution of length. Produce means that rotation is produced by a column of solution of length. We take length is 1 decimeter and containing 1 gram of substance per cc. of the solution under experimental condition, that is temperature of solution for the wavelength used. So what we take, like if I have something like this, we'll take length of solution because light has to pass, so through how much thickness it's passing, that is important, that we denote as L, length of the solution column in centimeter. Then what is the concentration of the solution, that is also very important, we define in gram per cc. Okay, and the specific rotation S will depend on how much the plane polarization is rotating divided by this length in decimeter and then concentration. So this is the dependence of how much the rotation will happen. So it depends on, then we get the specific rotation value of that optically active material. So when we do this, and then so this, when we write in simpler form, this will become tan theta divided by LC. L is length of solution through which it has to pass, and C is the concentration. So if we plot a graph, we'll take this measurement for different concentration value, and we'll get different thetas. Then because S is depends on a material, so S will be constant, variation will be in theta and C. Then we'll get a straight line curve like this, okay, which will represent the slope, and from slope we'll be able to find the specific rotation value for this. So this is known as calibration curve. So this was the theory behind polarimetry experiment, and the experiment was demonstrated by a professor in the videos. You can go there for details. And yeah, so there we were using a Nicol prism. As I said, we use it for polarizing a light. So we were using Nicol prism as a polarizer. Then this was the tube which contains our optically active solution, through which when the light passes, it's plane polarization. Through Nicol prism, when it passes, it becomes polarized here itself. Just to make it clear, the light from the source is unpolarized, and after passing to Nicol prism, because it's a polarizer, we get polarized light, plane polarized light. Okay, and when it passes through this optically active solution, then its plane of polarization changes by some angle that we analyze using again Nicol prism. Now here it acts as analyzer, and then we detect it through eyepiece. In between we have kept Lorentz half shade. What it does, it just helps in the experiment because it ensures that we get a very good intensity of because otherwise when we'll be analyzing, when light is coming at certain angle, initially if the axis of Nicol prism as polarizer and analyzer, if their optics axis are parallel, then the light will pass. So when the optics axis of this analyzer will change 90 degree corresponding to polarizer, then the light should completely cut off and we should not get anything. But if you watch the lecture video again, there in detail it's explained that how this thing works to get us very good intensity of light, and otherwise the light is not completely cut off, so it's difficult to find at which angle exactly it's getting completely dark or something. So to get good intensity and good darkness, we use this Lorentz half shade, and this gives us so when we rotate that thing through this 360 degree, we'll get 4 times high intensity and 4 times darkness kind of thing. So this was the basic of the experiment. Okay, now there was another experiment. This we had discussed 2 weeks back about Fresnel's zone. This we had discussed under something known as Fresnel's diffraction. That we know we have Fraunhofer diffraction and Fresnel's diffraction. Fraunhofer diffraction we discuss when our object or image or both are at infinite distance. But Fresnel's diffraction is when either image or object, both image or object are at finite distance. That time that diffraction is known as Fresnel's diffraction. So under this we were discussing about these zone plates, that these are basically created by, okay, let's see, so they look something like this, but if we zoom this area further, we'll see that this is made up of, this is not completely transparent, this inside, even this has alternate concentric circles or concentric rings, where one part, alternate part is transparent and alternate part is dark. So what we get out of this is, just to recall, this we had discussed actually last week, but here because we are again discussing this, so this is from last week itself, that this Fresnel diffraction, we were, as I said, that this diffraction we consider when either the source of light or observing screen or both are at finite distance. Okay, now from this Fresnel diffraction we had seen that this kind of aperture we can have here, circular aperture, where the pattern obtained on the screen could be like this. Here, even though the center of this aperture is transparent, but the diffraction pattern that we are getting, it may have darkness at the center. This happens because the lights from diffracting from the edges of these obstacles are diffracting, and that's why we are getting bright and dark alternating zones. These things we have discussed and also were there in lecture in detail, so I'll just go fast here. Other kind of aperture could be something like this, but for say this also we'll get alternate dark and bright ring kind of pattern, and we wanted to understand why this is happening. So when we consider a circular wavefront of light, and then we see that it may have different these circles, and light reaching from the circular wavefront to P point, will the consecutive these zones will have will be out of phase with each other. Because of that, the light reaching here, we were seeing its intensity will vary something like this. So the intensity from the center zone will be A1, the next zone will be A2, but since it will be out of phase, the amplitude will be subtracted. The next one will be in phase, then next one will be out of phase. So the total amplitude reaching P will be A1 minus A2 plus A3 minus A4 and so on. If there are m number of zones, then the intensity at the screen or the P point will be A1 by 2 plus AM by 2. But if m is even, it will be given by this. So these are the different zones. So what we understood, that if on that circular wavefront, I'm imagining those zones right now, okay, and saying that the path difference between them is lambda by 2 consecutive zones. The path difference of light coming from consecutive zones is lambda by 2. So one amplitude from one zone is getting added and next zone is getting subtracted. But see, if somehow I take only these additive amplitudes and somehow I can stop the subtraction of these alternate amplitudes, then all these amplitudes will get added and I'll get a very high intensity on the screen. How we can do this is, whichever zones for which we are getting this subtracted amplitude, if we make them black so that no light comes from those particular zones, then what we will get here is added, see, we have these zones kind of, this is what we I was showing you, zone in Fresnel zone, that picture I showed you, these rings. We are darkening actually those zones from which we may get destructive path difference of light. So when we do that, if we'll keep all the zones transparent, then at the center, or if we keep all the zones transparent, then at the screen, which is our point P, we'll get A1 amplitude. But if I keep all them, if the light is shining on all the zones, then I'll get A1 by 2 minus A2 by 2 plus A3, sorry, A1 minus A2 plus A3 minus A4 kind of, this kind of thing, right? Now if I am darkening second zone, fourth zone, sixth zone, then what I'll get is A1 plus A3 plus A5 and so on, or A2 plus A4 plus A6 and so on. That means intensity will be many times higher. And then this zone plate will be acting like a convex lens. Because for convex lens also what happens, whatever source of light is coming, it falls on convex lens and everything gets concentrated at a point. Here the intensity is higher. So something similar the zone plates are doing, because we are able to get rid of the amplitudes of light that are destructive in nature. So we are only getting addition of these amplitudes from, not from alternate, but after leaving every one zone plate in between. So we are getting addition of these. Okay, so this is what we mean by half period zones and Fresnel zone plate, which works as a convex lens. But how is it different from the usual convex lenses? The convex lens that we use, which looks like this, it has only one focal length, the point at which it focuses the parallel beam. We call it focus point, and the length from optics axis of the convex lens to that is called focal length. But here for Fresnel zone plate, it has multiple focal length. This is the difference. Okay, so SM here is the radius of all these zone plates, which are almost same. I mean, area of each ring is same, but the radius depends like this. So again, this was the relation that we had seen last time. Now this will be A is the distance of the light source to the zone plate. B is the distance of the zone plate to the screen where the image is forming. So you can recall that it's something like when we were talking about convex lens, 1 over u plus 1 over v is equal to 1 over f, where u is the distance of object from the lens, v is the distance of image from the lens, f is the focal length. Here also we are getting something similar. When we rearrange this and write like this, then we see this is like 1 over u, 1 over v, so it is also equal to 1 over f. So from this we can find out focal length. Now we can see focal length is depending on the even for particular zone, depending on the wavelength we are using, the focal length of that zone plate will be changing. Okay, so this is what I was saying, that but for normal convex lens, it doesn't matter whichever wavelength you are using, the focal length of the convex lens will remain same. But here for the zone plate, although it acts like a convex lens, its focal length is depending on wavelength, or if wavelength is constant, then depending on the order of zone plate, right, first zone or second zone or mth zone, the focal length will change. So here it has multiple focal length, this Fresnel zone plates. And then here also we can plot a graph between 1 by m, that is the order of zone plate, and then focal length, we will get a straight line like this. Okay, so this was the things that were there, and mostly this week more lectures were there on the experiment. So for experiments, you can go and just to see everything is going on. Yeah, you guys can go and watch in the lecture videos, and if there is doubt, you can let me know through email, or you can ask in the next doubt session also. So now I think we can start with discussing the numericals based on these things. So we have a lot of numericals based on transmission grating that we had started discussing last time, and this week's assignment also I saw there are many questions based on transmission gratings. So we'll do a lot of numericals on that, and then we'll do numericals based on zone plate as well. So this will really help you guys to do your assignment questions due for this week. And so I'll start solving, and if you guys have any doubt, you can ask in between. Okay, let's start with the first question. So the question is, we have a plane transmission grating having 15,000 lines per inch. So we have 15,000 lines per inch, and it diffracts monochromatic light by 20 degrees. So there is a grating, light is falling on it, it's diffracting it by 20 degrees, and number of lines is 15,000 lines per inch, and it diffracts monochromatic light by 20 degrees in the first order. So we are talking about first order. Calculate the wavelength of light. Wavelength of light we need to find out. Okay, so recalling the condition for diffraction through grating for transmission grating, the condition for getting maxima is a plus b sine theta, where a and b is what? A is like, if a is the gap, then b is the opaque this. So a plus b is the distance between two gaps, kind of consecutive gaps. So d we call grating element. So here grating element is a plus b. So grating element, if I'll calculate here, grating element, which is a plus b, that will be what? That is 1 over number of lines. Here number of lines is 15,000 lines per inch. 1 inch is 2.54 centimeter. That means 15,000 lines per inch. This means 15,000 lines per 2.54 centimeter. Okay, so grating element will be 2 point reverse of this, 2.54 centimeter divided by 15,000. This will be grating element. Now if I convert centimeter into meter, then this will be 2.54 10 to the power minus 2 meters divided by 15,000. This is grating element. Oh, so the condition was a plus b sine theta is equal to n lambda. Lambda is the wavelength of light, sine theta, theta is the by how much the diffraction is happening, a plus b is grating element, n is the order. So when we substitute these values here, 2.54 times 10 to the power minus 2 divided by 15,000, this is a plus b grating element, sine 20 degree, and the order of light we have to consider is first order, so n will be 1, and lambda we need to find out. So when we calculate this, we'll use scientific calculator, because your exam is also online. You will be getting scientific online calculator that I'll show in extra session if we get to take that. I'll tell you how to use those things. So yeah, calculator I'll use here. 2.54 times sine 20 degree divided by 15,000 is 0.000579154 multiplied by 10 to the power minus 2. 10 to the power minus 2. So it will be 1, 2, 3, 4, 5, 5.79154, 10 to the power minus 3. Wait, this I converted into meters. This one is right now. Wait. Here 10 to the power minus 1. This is right now in meters. If I write it better way, it will be 1, 2, 3, 4, 5. Means 10 to the power 5. 10 to the power minus 5 and 6, 7. Minus 7 meter. If I take will be 5791.54. Is there some mistake? That's 9.54. Okay, so this 5791.54, then it will be 10 to the power minus 10 meters. Answers here are in angstrom. So in angstrom it will be 5791.54 angstrom. Okay, so the correct answer here should be 5791.54. So the correct answer is close to option A, 5790. Because others are 59075. Yeah. And the closest value is A. A is the correct answer here. Okay, moving on to next question. How many orders will be visible in a grating? Again, the question is on grating, which has 4,000 lines per inch. Okay, let's convert inch to some known length unit. So that 4,000 lines per inch means 4,000 lines per 2.54 centimeters. Then it's a grating, so it will have opening and then it will have opaque length. So total A plus B will be the grating element. This we call grating element. So grating element will be 2.54 divided by 4,000. This will be centimeter. Okay, this is grating element. So this is the grating element of this grating. Wavelength of light we are using is 6,000 angstrom, and we need to find out how many orders of light how many orders of diffraction pattern we'll be seeing. So the condition is A plus B sine theta is equal to n lambda. Lambda we know here, A plus B we know. Now, depending on theta, there will be different direction in which the light will be diffracting, and we will be getting different order of diffractions. Now, how many orders are possible here if the grating element is this and wavelength is this? What is the maximum number of order? How many orders will be visible? Okay, so here you can see that sine theta value, we know sine theta maximum value it can take is 1. Its value actually goes between 0 to 1. So maximum value it can take is 1. Now A plus B is fixed. Lambda is fixed. So only thing that can change is theta and accordingly n. So n will have maximum value when this is constant. A plus B over lambda is constant. N will be maximum if sine theta is maximum, right? So n maximum will be something like this plus b lambda, because sine theta maximum will be 1, so n maximum will be something like this. Okay, so n maximum will be A plus B over lambda. Now A plus B, which is the grating element, it is like this, 2.54 centimeter. If I convert into meter, it will be 10 to the power minus 2 meters divided by 4,000. Okay, and then lambda is 6,000 angstrom, 10 to the power minus 10 meters. Now when we calculate this, then we'll get, so n maximum will be less than or equal to this. So when using calculator, I'll calculate this thing, 2.54 2.54, just 2.54 divided by 4,000 divided by 6,000. This will be 1.0583, 10 to the power minus 7. We have 10 to the power minus 2 plus 10. So this will be 10 minus 2 means 8, 8 minus 7 means 1, means 10.583. So the order can be less than or equal to this. So it cannot be 0.5. So that means the maximum order possible here is 10. Maximum order possible for this particular wavelength and for these number of grating elements, the maximum order possible is 10. So the correct answer here is option D, which is 10. Next question. In a plane transmission grating, the maxima of order 3, 6, 9, etc. are missing. What is the ratio of width of a ruling to the space between the rulings? What do we mean by width of ruling to space between the rulings? As I said, we have n number of slits in this openings in the screen or the slit. If say this ruling is B and A is the gap between these rulings, A is the spacing between these rulings, right? If this is A or this is B, kind of, this one, and this will be become D, grating element. So let's say B is the width of a ruling, A is the space between ruling. Then the condition for, we know in the screen, light is coming from this side, let's say, and on the screen we know we'll be getting diffraction, interference pattern due to diffraction, and then in between the interference, diffraction because of, the pattern due to diffraction and also the pattern due to interference of the fringes. They will be overlapping, and then diffraction minima also will have some interference peaks which will get missing because of this maxima of interference will be missing. These we had discussed in last videos, weeks lecture time. So what happens is interference condition for interference maxima for these kind of gratings are given by A plus B sin theta is equal to n lambda, where n can be 0, plus minus 1, plus minus 2, and so on. Now, diffraction minima, the condition for diffraction minima is, condition for diffraction minima will be A sin theta is equal to m lambda, okay, where m will be plus minus 1, plus minus 2, and so on. Okay. Now we know if the minima of diffraction here, like is minima of diffraction, if it coincides with maxima of interference, then those interference maxima will be missing, which is happening here. And then we had also known that then we can write the ratio of interference maxima and diffraction minima, and we'll get n lambda over m lambda. Okay, so it's relation between A plus B, A, and n over m. That means from this we can say as A plus, so this, from this we can say that n can take value A plus B over A times m. Hence the, hence the missing orders will be, when I'll keep m is equal to 1, I'll get a plus b over a. When we'll keep m is equal to 2, we'll get 2a plus b over a, and so on. Okay, I'll have a slide here. Just ensure. So these will be the missing orders here. Now further, since it's given that the orders that are missing are 3, 6, 9 and so on, so we'll equate them here. And we also saw that the missing orders are these. These are the missing orders there. And it's given in the question that the missing orders are order 3rd order, 6th order, 9th order, etc. From this we can calculate this. We'll get a plus b is equal to 3a. It implies that b is 2a. Okay. b is equal to 2a. That means the ratio here b to a is 2:1. And in the question, you have to find out the ratio of width of ruling to space between the rulings. So the ratio is 2:1. So B is the correct answer. So next question, question number 4. It's a light with wavelength 530 nanometer falls on a diffraction grating. Again, it's a question of diffraction grating with grating element. So now grating element is given directly. Grating element value is 1.5 micrometers. Find the angle at which the maxima of highest order is observed when light falls on the grating normally. So when light is falling normally, you have to find the angle at which the maxima of highest order is observed. So first we'll see what is the maximum order possible when lambda is 530 nanometer and grating element is 1.5 micrometer. Then we'll see for corresponding to which angle we'll obtain that highest order maxima. So first, again, starting with what is the condition for maxima. So that is a plus b sine theta is equal to n lambda. From this, sine theta will be n lambda divided by a plus b. N, now lambda is 530 nanometer, 10 to the power minus 9 meters. A plus b is 1.5 micrometer, means 10 to the power 6 meters. Both are meters, so it will be cancelled. So from this, we will get n times. Let me see. Divided by 1.5 will be 353.33, and these exponents minus 9 plus 6, that will be 10 to the power minus 3. So this will be n times 0.353. So sine theta can take these values where n will be 0 or plus minus 1 or plus minus 2 and so on. So the maximum value we want to find out what is the maximum order possible. Now we know again sine theta can take maximum value 1 and minimum value 0. Maximum value can go up to 1. So if I take n 0, then it will be 0, which is the minimum value. If I take n is equal to 1, then sine theta will be 0.353. If I take n is equal to 2, Sine theta will be 2 times 0.353, which is 2 times 0.353 is 0.706. If I take n is equal to 3, then sine theta will become, let's see what value we get, 3 times 0.353. Okay, so now the sine theta value is becoming 1.059, but we know it's not possible because sine theta maximum value is 1. Okay, so that means this n is equal to 3 is not possible, so the maximum order we will see here is n is equal to 2. Okay, so the maximum order possible for this lambda and this grating element is 2. So the maximum order that we will be able to see will be second order diffraction, and at which angle it will happen. So for that, for maximum order, the sine theta will get value 0.706. So maximum order, which is n is equal to 2, the value of sine theta will be 0.706. So when we will take sine inverse of this, we will get 45 degree. Using calculator we have to find out this, we will get 45 degree. So at 45 degree diffraction we will be getting second order, which will be the maximum order diffraction. So the correct answer for this question is B, 45 degree. Next question. If the width of a ruling is half the spacing between the ruling. Okay. Let's consider that E is the width of ruling and A is the spacing between the rulings. Okay. And if width of ruling is half of the spacing between the rulings, this is given, then the absent spectra in a grating. So in this grating again, due to interference, we'll have maxima, and then due to diffraction, we'll have minima, and when they overlap, then these interference maxima will be missing. So from there we'll check what will be the orders which will be absent here. So using the condition for interference maxima and diffraction minima, so for interference maxima the condition is A plus B sine theta is equal to n lambda, and for this for diffraction minima it's A sine theta is equal to n lambda, where n can take 0, plus minus 1 and plus minus 2 and so on. M can take plus minus 1, plus minus 2 and so on. Okay. Now when we'll take ratio of this, then we'll get A plus B sine theta divided by A sine theta is equal to n lambda over n lambda. This will we'll get rid of sine theta here, lambda also, and we'll get A plus B over A is equal to n over n. This shows us that n can be A plus B over A times n. Now for, that means with m is equal to 1, and absent spectra will be, because this condition happens when they are overlapping, the interference maximum and diffraction minimum. So when this condition is happening, that means the absent orders will be a plus b over a plus b over a times 2, a plus b over a times 3, and so on. Okay. Now we know this condition that width of ruling is half of spacing between rulings. So using this, now if b is a by 2, that means when we will substitute here, a plus b by a will become a plus a by 2 divided by a, which is 2a plus a, that is 3a by 2 divided by a, means 3 by 2. Similarly here it will be 6a by 2, this will be 9a by 2. So the order here will be so the missing spectrum will be 3 by 2, 6 by 2, 9 by 2. Hence the missing orders here will be this. These will be the missing orders. Okay. Question number 6. Light of wavelength 500 nanometer is incident normally on a plane transmission grating with width 3 centimeter. That's the width, and the lines are 15,000 lines. Okay, so this is not the width of spacing, this is the width of grating. The whole grating is this. That means the grating element will be so that means 15,000 lines per 3, on 3 centimeter. That means 15,000 lines per 3 centimeter. So grating element will be 3 divided by 15,000 centimeter. Find the angle of diffraction of the first order maximum. For first order maximum, we need to find the angle of diffraction. So again, using the condition of interference maximum in lambda, n is 1 here, a plus b is 3 over 15,000 multiplied by sin theta. Lambda is 500 nanometer. Putting it to a meter, it will be 10 to the minus 9 meter. This is in centimeter. If this also we convert to meter, 10 to the power minus 2. So here sin theta will be 500 times 10 to the power minus 9 multiplied by 15,000 divided by 3 times 10 to the power minus 2. This will be 525, and this will be minus 9 plus 2 means minus 7. So it's 25 and 10, 3, 4, 5, 5 minus 7 is minus 2. Means 0.25. Theta will get sine inverse of 0.25, which will be sine inverse of this will be 14.5 degrees. The correct answer will be 14.5 degree. Option B. Next question is light with wavelength 600 nanometer falls normally on a diffraction grating, again inscribed on plane surface of plano-convex lens. So we have a plano-convex lens. On one of its side we have this diffraction grating made as shown. The radius of curvature of the plano-convex lens is 20 centimeter. The grating element is 6 micrometer. Find the distance between the first maxima in the focal plane of the lens. So we know at the center we'll have bright intensity, then at distance of x from the center on both sides we'll have next first maximum, because this is zeroth order. First maximum we'll be getting on either side after from this on the plane of convex on the focal plane. So what do we mean by focal plane is that when we have a convex lens like this, we know this is its optics axis and all the parallel light coming will focus at a point. That point we call is focus, and the plane passing through that focus is called focal plane. Okay, so focal plane is parallel to optics axis. This is optics axis, and this focal plane is perpendicular to this optics axis, and this is optics axis. So we need to find out this x. There we have to consider b is the width of tooling and a is the spacing between the rulings. So we want to find out focal length. Usually from mirror we know focal length is half of radius of curvature. Here because it's a plano-convex lens, that means it's not double convex lens, it's plano-convex lens. So this formula is for this. The formula for focal length of plano-convex lens is given by this. Okay, refractive index -1 divided by radius of curvature. So according to this formula, the focal length of this plano-convex lens will be, so refractive index is 1.5. 1.5 minus 1 divided by radius of curvature, which is 20 centimeter. So focal length will be 0.5 by 20 centimeter inverse. Wait, sorry. F is R by 2. Here this is 1 over F. 1 over F. F will be 20 divided by 0.5 centimeter. This will be 20 divided by 0.5, which is 40 centimeter. So focal length of this, first we found, because we'll need this. So focal length is 20 centimeter. For the condition for interference maxima, now will be A plus B, where A plus B is the grating element, sine theta is equal to n lambda. Now for first maximum, because we have been asked to find out the distance between the first maximum. For first maximum means n will be 1. So here sine theta will get lambda over A plus B. Lambda is 600 nanometer. Converting into meters, it will be 600 times 10 to the power minus 9 meters. Divided by grating element is 6 micrometer. 6 micrometer means 10 to the power minus 6 meters. So it will be 100 10 to the power minus 3, means 0.1. So theta will be sine inverse of 0.1. Theta value we will get is 5.74 degrees. Now we want to find out the distance between the first maxima, distance between the first maximum that we are getting on either side. So that means 2x we want. Now we take this theta, okay, and this is x, then we know tan theta is x by this, which is focal length, right? Because we will get the image at the focal length. So this will be the formula we'll be using. So tan theta is equal to x by f. Using this, we will get x will be f times tan theta. So now we want to find out the distance between first maximum in focal plane of lengths. That means it will be 2x, that means it will be 2f tan theta, means it will be 2 times the focal length we calculated was 40 centimeter, 40, and tan of the angle that we found out was 5.74 degree. 5.74 degrees. This is 5. When we calculate all this, we have 40 times 2 times tan of 5.74 degrees means 8.04147 should be in this will be centimeter. So the correct option here, why is it in centimeter? Because the focal length here is in 40 centimeter. So this will also came out in centimeter, and the correct answer will be 8 centimeter. Option C is correct. Okay. So the question number 8 is, if the radius of the first zone is R0, then find out the primary focal length of a zone plate for bright image. So we know this one condition. For Fresnel zone plate, we had derived, and the condition is 1 over u plus 1 over v, which is equal to 1 over f is equal to 2m plus 1 n times lambda divided by Rn square. And Rn is the radius of that particular zone, n is the order of that zone, lambda is the monochromatic wavelength that we are using. Okay, so also here u is the distance of object from zone plate, v is the distance of image from the zone plate, and f is the focal length of that zone plate. So using these conditions, we see that focal length formula will become, when we will take reciprocal of this, it will be Rn square divided by 2m plus 1 times lambda. Because it's this zone, Fresnel's zone plates are multi-focus, they have multiple focal lengths. That's why we are taking this n here, and this m is the order of the zone plate. So we are using this formula, and now we know that this also we had seen that radius is actually proportional to the order of the zone. That means we can write using some constant, we can write like this. We need to find out the focal length of a zone plate, primary focal length. That means for n is equal to 1, the radius is given to be R0. That means we will get K. For primary focal length, m will be 0, be 0. So F will be R naught square divided by 2 times 0 plus 1 times 1 times lambda, which is a that also we don't know. So the formula will be like this: R naught square, this will be 1 times lambda. So the focal length will become R naught square by lambda. C is the correct option. Next question, question number 9. The question is, to make a zone plate, circles of radii 10 cm, 10 root 2, 10 root 3 centimeters are drawn, and subsequently 100 times reduced photograph of it is taken on a photographic plate after painting the alternate zones. So we are painting the alternate zones, and first we made radius of these different radii value to make Fresnel zone, and then the alternate zones we are painting, okay, and we are reducing that 200 times. Find the distance from the zone plate at which the primary image is formed when an object is placed at a distance of 10 meter from the zone plate. So we have zone plate, alternate dark and bright discs are there. Distance of object from zone plate is 10 meter. This is our view. Need to find the distance from zone plate at which the primary image is formed. So primary image distance, because corresponding to different zone order, we will be getting images at different focal length. We need to find out the distance of image for the primary image. Okay, so we need to find out B. Lambda is given and image distance is given. We need to find out focal length here and radius, and then we'll be able to find the distance of primary image. So the radius of first zone, we made the radius 10 centimeter and then we reduced it to 100 times. That means the radius of first zone R1 will be 10 centimeter divided by 100. That means 0.01 centimeter. So 0.1 centimeter, this will be, okay, 0.1 centimeter. Yeah. This is the radius of first zone. Now again using the formula of focal length, R1 square divided by 2m plus 1 times lambda. Since focal length for primary image will be m is equal to 0. So f will be r1 square, m is equal to 0 will be r1 square over lambda. Value of this r1 is 0.1. If I convert it into meter, 10 to the power minus 2, and square of that divided by lambda, which is 6000 angstrom. 6000 angstrom, if I convert it into meters, it will be 6000 10 to the power minus 10 meters. 6000 times 10 to the power minus 10 meters. This both are in meter. And this is in meter square, this is in meter, so we'll get in meter. So answer will be 0.01 10 to the power minus 4 divided by 6000 10 to the power minus 10. So it will be C 0.01 divided by 6000 or 0.01 divided by 6 0.00167. This will be 10 minus 4 will be 6. 6 minus 3 will be 3. 10 to the power 3 meters. 1, 2, 3. That means 1.67 meters is the focal length. Okay, so we found out the focal length. One more slide. 0.67 meter. And now using this formula, because we know the object distance, now we know the focal length, so we'll be able to find out V, putting the values here. So 1 by V will be 1 over F minus 1 over U. So 1 over F is 1 over 1.67 minus object is a distance of 10 meters. 10. When we'll calculate this, we'll get 10 is 1.67 divided by 16.7. We'll get 0.5. So we will be inverse of this. We will be getting, did we do some mistake? 1 over F will was correct. So 1 over V will be 1 over 1.67 minus U is 1 over 10. Let me just check. 1 divided by 1.67. 1 divided by 1.67 is 2.598, and this is 0.1. We'll subtract with 0.498. 1 divided by 0.498. So we'll be getting V, this is 1 over V. So V will be 2.00481. Okay. That means V we can write as 2 meters. So the primary image will be formed at 2 meters. The correct answer is 2 meters. Okay. Next question, question number 10. Again is on zone plate. So we have a zone plate which produces primary image and first secondary image at a distance of 30 centimeter and 6 centimeter respectively. Means produces primary image at 30 centimeter and first secondary image at 6 centimeter from the zone plate. So this is like V0, this is like V1. Calculate the distance of object. We need to find out distance of object from the zone plate. Okay. So by construction of zone plate, we know the formula again, that Rn square is some constant in this. That constant is Rn square over n, where n is some natural number, and so on. Now focal length, we know focal length in this relation. Focal length is given by Rn square divided by n lambda 2m plus 1. Okay. For primary image, m will be 0. So for primary image, focal length will be Rn square divided by, this will be 0 plus 1 means 1, n lambda. K by lambda. Now for, I have to take for first focal length will be k over 3 lambda. Okay. Now for first case, that is for primary image, the relation will be 1 over u plus 1 over v0 is equal to 1 over, or then I should call this, let's call this v1, let's call this v2, let's call this v1, so it will be f1, okay, which is equal to lambda by k that we have seen for first secondary image. 1 over u plus 1 over v2 is equal to 1 over f2, which is equal to 3 lambda by k. This is our second relation. Now when we will substitute equation 1 and equation 2, okay, we'll get, substituting equation 1 in equation 2, we get, okay, slide. So when we'll do that, we will get 1 over u plus 1 over v2 is equal to 3 times, and lambda by k value we'll substitute from here. Okay. So it will be 1 over u plus 1 over v1. And now 1 over u we need to find out, v2 we know. What is v2? So v2 is 6 centimeter, v1 is at 30 centimeter. v2 is 6 centimeter, v1 is 30 centimeter. And we solve this further, get this 3 by u plus 3 by 30, which is equal to 3 by u plus 1 over 10. So 3 by u, I'll take it this side, 1 over 6 minus 1 over 10 is equal to 3 by u minus 1 over u. This will be 2 over u, and on left hand side it will be 10 minus 6, 2 by u, which is equal to 4 by 60 is equal to 2 by u. This implies that u is 2 times 60 divided by 4 centimeters. Oh, wait. So v was in centimeter. Yeah. Okay. So this will be, this will be 30 centimeter. So the object distance is 30 centimeter. This is the correct answer. So okay, these were that we were solving based on this week's lecture by Professor Das. And if you guys have any doubt, we can discuss, or we can close this session and we'll meet next week with some other kind of experiments and their concepts. Today we discussed these. We had review about what we did last week, which included plane transmission, grating, zone plates, polarization, and then today we discussed about how we can polarize the unpolarized light, various techniques used, various devices used, and polarimeter, what is it, how we can find out refractive index for O-ray and E-ray by using a prism made up of these uniaxial anisotropic crystals, and zone plates, and we did numericals based on this. So if there are no questions, I'll close the session.